In the discussion of this chemical thermodynamics, today I shall discuss the lecture 28, expression of chemical potential. Chemical potential could be expressed in terms of the partial pressures, total pressures, mole fractions for the ideal system, for the non-ideal system, for an ideal gas and for real gas, etc. I have already discussed the chemical potential is a very important thermodynamic property in chemistry. Not only it is equally important in physics also. Chemical potential is a measure of the escaping tendency of a substance from the region of higher chemical potential to the region of lower chemical potential. So naturally this chemical potential can be very useful criteria for the spontaneity of a process occurring at constant temperature and pressure. I have already discussed, you probably know that del mu by del P at constant temperature is equal to V bar. V bar, this is the change of chemical potential with respect to pressure at constant temperature. That means the effect of pressure on the chemical potential. V bar is the molar volume of the substance. If we take this pure ideal gas, then V bar equal to RT divided by P. This is a very simplest most case, and so del mu by del P at a constant temperature is equal to RT by P. P the pressure, T the temperature, and or I can write this d mu equal to RT and dP by P. At constant temperature, if we try to express the influence of this pressure on the chemical potential at the constant temperature, then it will be, let us take this integration, and we can do the definite integration. It is 1 atmosphere, and when P is 1 atmosphere, chemical potential is mu 0, means a standard chemical potential. Standard chemical potential is the potential of this 1 mole potential of this ideal gas at a given temperature and pressure 1 atmosphere. And when P atmosphere, upper limit, and so it is mu. If we do this integration, then mu equal to mu naught plus RT ln P. And this mu naught is the standard chemical pressure. If we write explicitly, very elaborately, then it will be mu is a function of temperature pressure, so it could be written as temperature pressure, and mu naught is a function of temperature only, and plus RT ln P. P is the pressure. So naturally, if we draw this curve here, ln P along this x-axis, and mu Tp along this y-axis, then it will give you a straight line. Here ln P equal to 0 means P equal to 1 atmosphere. So with this increase of pressure, the chemical potential of this ideal gas is also increased. This can can also be illustrated with an example how this pressure measures the chemical potential. Suppose here these two gases are there, two gases. It is the barrier or the partition. Here the pressure is P1, here the pressure is P2. Both are having the same gas, say hydrogen gas in both the compartment. It is P1, it is P2, and temperature say at a T, and P1 is greater than P2. That means it is this gas here remains at high pressure, it is at lower pressure. So they are totally separated by this partition. If we make a hole at this partition, then the gas will move from this high pressure to this lower pressure until it becomes equal. Since this is the condition for the mechanical equilibrium, this instead of expressing this spontaneity of this process in terms of this pressure, we can also express in terms of chemical potential. Means here suppose chemical potential is mu1, here it is chemical potential mu2. Since P1 is greater than P2, then mu1 is greater than mu2. So instead of saying this pressure, we can also say this substance. Here not only this gas, any metal will move from high chemical potential from a region of high chemical potential to the region of lower chemical potential spontaneously at a constant temperature. So this chemical potential is very important. If we do this, not this pure ideal gas, but it is the a gas in ideal mixture. In ideal mixture, then this equation, the same equation will be changed as mu I, and it is Tp, means the chemical potential of the ith component. Suppose this gas is ith component, this ith component of this gas remains in a mixture, and this one also will be equal to mu I naught at a temperature T plus RT, and in this case ln Pi is the partial pressure of this gas of the ith component in this mixture. So in this case, so this is also another expressions of the chemical potential in terms for a ith component of a gas in ideal gas mixtures. So we can write here mu I and Tp equal to mu I naught at this temperature T plus RT ln Pi. Pi is the partial pressure. Sometimes or very often this Pi is replaced in terms of the mole fractions according to the Dalton's law. According to the Dalton's law of partial pressure, we can write Pi equal to this Xi into capital P. P is the total pressure of this gas mixture. Pi is the partial pressures of this ith component of this gas, and Xi is the mole fraction. So whenever this Pi is replaced, when Pi is replaced by this Xi into P, then it will be mu I Tp equal to mu I naught into T and plus RT ln P. P is split up. P, this Xip they are putting, and this whenever it is split up and it is taken in a bracket, plus RT ln Xi, and here at a given temperature pressure these two are constant, so it could be written as mu I naught, temperature, pressure both are variable here, plus RT ln xi. This one is not the standard chemical potential of the ith component, but it is the standard, it is the chemical potential of this ith component when it remains in pure state, means xi equal to 1 at a given temperature pressure. Whenever the pressure is taken 1 atmosphere, this mu I not T, whenever the P is taken as 1 atmosphere, this is identical with this standard chemical potential. So from this relation, it is quite evident that in a gas mixture, this xi is less than 1. The limit of xi is greater than 0 and less than 1. So xi less than 1 means ln xi is less than 0, means negative. So this term is fully negative. So this one is greater than this one. We can write this mu I naught at a temperature pressure is greater than mu I at T and P. Very interesting actually. Whenever the gas remains in pure state, the chemical potential at the same temperature pressure, the chemical potential is larger or greater than the chemical potential of the same component when it remains in a mixture. Whenever that gas remains in a mixture, the randomness is increased, and this randomness is increased means entropy is increased, and this increase of entropy actually lowers down the chemical potential of this ith component in this mixture. So this could be also shown one illustration, say this conclusion. Suppose here these two gases are there. Here two compartments are there. Here it is the compartment. Here hydrogen gas remains in pure state. Hydrogen gas remains in pure state, and it is also at a pressure P, and here it is hydrogen gas plus nitrogen gas in a mixture. In a mixture, it is also the pressure P. Both are at the same pressure and both are at the same temperature, and these are being partitioned. Here only the nitrogen gas in pure state. This one is the hydrogen gas and nitrogen gas in a mixture. See, the gas is in an ideal mixture. Taking the ideal mixtures of these two gases, and if we take this partition, suppose a very thin palladium metal foil in which the hydrogen gas can move, can flow, can permit. Hydrogen gas will be permeable through this thin palladium metal foil. If this partition is inserted, then hydrogen will move from this side to this side. This reason for both are having the same pressure. Here the hydrogen gas in pure state, here the hydrogen gas in a mixture. So here the chemical potential of this hydrogen in pure state at this temperature AP is greater than chemical potential of this hydrogen at the temperature pressure in this mixture. So this one is greater than this one. As you know, the chemical potential will move from the higher region to the lower region from a state of the higher chemical potential to a state of this lower chemical potential. So automatically hydrogen will move through this thin metal foil. This is another illustration of this equation. Osmosis could also be expressed by this way. So another thing is that whenever the two ideal gases are being mixed up, or several ideal gases are mixed up, its free energy will decrease, and change of free energy could be expressed. Say delta G mixing whenever the two gases or the more than two gases are being mixed up, its free energy due to mixing is decreased. Delta G becomes negative. So this could be expressed as, suppose here the two gases, suppose we have taken here the gas number 1, here the gas number 2. Two gases are there. Here it is N1 mole number, here it is N2 mole numbers, and these two are being mixed up through this hole. So what will be the same pressure, same pressure and same temperature in both the cases. So what will be the value of this delta G mixing in this case? That we can calculate by using the expressions of the chemical potential. So it will be G before after mixing and divided by minus G before mixing. So this will be equal to after mixing, it will be N1 mu1 plus N2 mu2, and before mixing it will be N1 mu1 naught plus N2 mu2 naught. They are remaining in pure state for these two gases, and this one written as N1 and here mu1 naught plus RT ln x1 plus N2 into mu2 naught plus RT ln x2. This sum of these two is the free energy after mixing, and minus before mixing it is N1 mu1 naught plus N2 mu2 naught. If we do this simplification, so then this one and this will be cancelled, and it will give you this N1 RT and ln x1 plus N2 RT ln x2. If we divide this 2 by the total number, say n equal to n is the total number, n1 plus n2, then it will be, suppose n, and here n1 by n and RT ln x1 plus n2 by n RT ln x2. So this will give you this. This one is the mole fraction of the first component. This one is the mole fraction of the second component. So n RT will get common, and it will be x1 ln x1 plus x2 ln x2. In general, we can write this delta G mixing. In general, we can write delta G mixing equal to nRT and summation of xi and ln xi ln xi. So this xi is fraction, so ln xi is negative. So this term, whole term on the right hand side of this expression is negative. That means this free energy change due to mixing is negative at a given temperature pressure, means the mixing of these two gases becomes spontaneous. So this from the chemical potential we arrive at when the mixing process becomes spontaneous. If we can calculate the entropy entropy delta S mixing, you can write minus del by del T at del here del G mixing at constant pressure. So whenever this delta G mixing is differentiated with respect to T, then T will be cancelled and it becomes a minus L R and summation of xi ln xi, and here it is minus. Again this xi is a fraction, so ln xi negative and negative, so this one is the positive. That means whenever these two gases are being mixed up freely, its entropy will be increasing, and delta S mixing it becomes a positive. Randomness will be increased whenever the two gases are being mixed up. And again, if we calculate this delta H mixing equal to delta G mixing plus T delta S mixing, and delta G mixing is this one and delta S mixing is this one, and multiplied by T negative, and so this becomes 0. So this conclusion are like that: the delta G mixing is negative, and delta S mixing positive, and delta H mixing 0, means there will be no heat change for these two gases, or the different gases, ideal gases are being mixed up. So these are the three expressions. We can also calculate at whenever equal mole numbers of these different gases are being mixed up, the free energy change becomes minimum, or the entropy change becomes maximum, or delta H mixing always equal to 0. So, and that could be done. Suppose we have the two gases, then in that case delta G mixing for the two gases equal to nRT and x1 ln x1 and plus x2 ln x2. x1 and x2, these are the mole fractions of these two gases in a mix whenever they are being mixed up, and N is the total number of moles of these two gases, T the temperature or the universal gas constant. If we write this x2 equal to 1 minus x1, if we put here the two variables are being substituted by one variable, then it will be this nRT and x1 ln x1 and plus 1 minus x1 and ln 1 minus x1. To get this value of x1 at which this delta G attains minimum value, we shall have to differentiate this one with respect to x1. So this del G mixing by del x1 at constant temperature pressure equal to nRT constant, and here these two variables, say x1 is differentiated with respect to x1, then it is ln x1, and plus when x1 written here and ln x1 differentiated with respect to x1 1 by x1, so x1 into 1 by x1 and plus in this case this one is differentiated with respect to x1, it will be minus 1 into ln 1 minus x1 and plus 1 by x1 remains intact. This one will give you 1 by 1 minus x1 and 1 by 1 minus x1 1 by x1 with respect to x1, it will be equal to minus 1. Power bracket close. So this one equal to nRT, and this one plus 1, and this one minus 1, plus 1, minus 1 will cancel. So this will be equal to ln x1 minus 1 minus by 1 minus x1, x1 by 1 minus x1. So whenever at which value of x1 this one attains minimum value, then in that case this one equal to 0, this one equal to 0. This one equal to 0. So this ln x1 divided by 1 minus x1 equal to 0, equal to ln 1 equal to 0. So x1 equal to 0.5 or half. Then x2 is also equal to 0.5. So it means that whenever equal mole number of these two gases are being mixed up, there will be minimum delta G mixing attains this minimum value. And in a similar way, it could be shown that delta S mixing attains maximum value whenever equal mole number of these two gases are being mixed up. Delta and delta H mixing will be always equal to 0. If we plot this three terms in a graph, suppose this is the graph. Temperature is constant, T and P is constant. Here this is the 0, this is positive, and this is negative, and here it is joule and mole inverse for these three properties. And for this free energy, this one is 0.5 for these two gases. It becomes 0.5. Here x1 0, here 1. This one is the delta G mixing by N, and this delta S will be like this one, and delta S mixing by N, and this is delta H mixing by N. So all these three values are plotted in a single curve. Delta G mixing attains minimum value whenever x1 is 0.5 for the two components, and delta S mixing by N also attains the maximum value whenever x1 is 0.5 equal mole number, and this is 0 all along. So this is the figure. Similarly, we can express similarly. Now I shall discuss very shortly, discuss in a very short way the chemical potential for the real gases. For the real gases, del mu by del P at constant temperature is equal to V bar. But this V bar is to be replaced in terms of temperature pressure for this real gas equations. This is not a very easy task, mathematically not very easy. And so instead of replacing this V bar by temperature pressure from this real gas equation, Jane Lewis have taken the same format as we have seen for this ideal gas, and mu Tp, in this case mu Tp equal to mu1 naught T plus RT ln F. He has written the same form as we have done. Instead of pressure J.N. Lewis introduced this new term, and this new term is called the fugacity. F is the fugacity. Fugacity of this gas is similar to the pressure. If we write this for ideal gas, then mu Tp equal to mu not Tp T plus RT ln P. So this is for the ideal gas, and this is for the real gas. So it is seen that both the formats are same. Instead of pressure for the ideal gas, we have used the fugacity F for this real gas. So F will be taken as this corrected pressure for the real gases, and fugacity having the same unit, same dimension as the pressures, same meaning, but it is not identical with this pressure. So actually F divided by P, it is equal to gamma. Gamma is called fugacity coefficient. Fugacity coefficient of this gas. And whenever the gamma is equal to 1, then when fugacity coefficient equal to 1, then fugacity and pressure both are equal, and taken the ideal gas behaves ideally. Whenever this gamma is not equal to 1, fugacity and pressure are not equal, and so there is a difference. So gamma could be expressed as e to the power Bp divided by RT, and this gamma could be expressed in terms of Bp by RT, where B is called second virial coefficient of this real gas equation. And for ideal gas, it will be 1 by RT into B minus A by RT for this ideal, for Van der Waals gas. For Van der Waals gas. So actually B depends on the coefficient of the constant in A and B of this Van der Waals gas, and T the temperature, and so B, if we put here for this gas whose A and B are known at a given temperature, then gamma could be known, and so this fugacity, in this case fugacity equal to P into e to the power B P divided by RT. Another term I can also use for the condensed state. Suppose for this liquid or solid, here it is the condensed state. Here it is condensed state, and here it is the vapor. So vapor is pressure P is the vapor pressure. So in this case, say one substance remains in liquid, one substance remains in solid, and it's vapor having the pressure P. Then as these two are equilibrium, so chemical potential of this one and this one are the same. So chemical potential of this condensed state of the substance is equal to mu naught T plus RT ln P. Here it is T and P. So this for the mixture, if the condensed several substances remains in condensed state, then it will be mu I Tp condensed state equal to mu naught I into T plus RT ln Pi, the partial pressures of this ith component in a mixture of this condensed state. If this could be also converted into this mu I Tp equal to mu I naught Tp plus RT ln xi in a similar way. So it is the chemical potential of the substance in condensed state, ith component at a temperature T and pressure P when it remains in pure state. For the real, this condensed state ideal behavior. If we consider this real condensed state, a slight variation should be there, and this mu I and Tp equal to mu I not Tp and plus RT ln AI. AI is the activity coefficient. AI is the activity of this ith component. AI is the activity of this ith component. Activity of the ith component in the condensed state. Activity of the ith component in the condensed state. Component. And this AI, actually AI equal to xi into gamma I. This one is called the activity coefficient. This one is called the activity coefficient of this ith component, and xi is the mole fraction, which is the activity of this ith component. There are several methods by which this activity coefficient could be measured, such as colligative properties, or the in ionic solutions it is best used in the Debye-Buchel equation, Debye-Buchel limiting law, etc. So this is all about the expressions of this chemical potential in terms of this partial pressures, in terms of this mole fractions, for the real system, for the ideal system, for the real system, for the ideal condensed state, for the real condensed state, and so on. Next, from my next class, I will discuss the solutions, and solutions I like to explain in a language which is much popular to the West Bengal students, in a Bengali. So Bengali and English, Bengali language and English language will be mixed up whenever we shall discuss these colligative properties of the dilute solutions and other properties of the solutions. That will be better for the higher secondary students in West Bengal and also IIT JEE if they know the Bengali language properly. Okay, thank you. Thanks for watching this video, and if you like, then please subscribe. Again, thank you.